In last class we have discussed about longitudinal and lateral magnification and also how to find the image location when there are multiple mirrors placed. So, we talked about successive reflections and how to find images in such a case. So, we will continue with that concept. So, today we will discuss about what would be the magnification produced when successive reflections happen. So, when we have two or more mirrors, let us consider two mirrors for now. So, if light gets reflected from each mirror and the final image which is formed, how much will be its magnification when compared with the object. So, that is what we are going to learn now. So, let me write it down like this: magnification due to successive reflections. Okay. So, let us consider a scenario where there is an object and light gets reflected twice. So, I will just take a general case, I will just represent it like this. So, this could be any device. So, this is device 1, let us say. So, it could be a plane mirror, it could be a convex mirror or a concave mirror. So, and let us consider one more device in this manner. So, device 2. So, these are two reflecting devices, let us say. Now, there is an object which is placed in between these two. So, let us say there is an object which is placed here and let us call the height of the object as HO. So, now in such a scenario, for example, let us consider the first reflection here and later on the image formed by this device will act as the object for this. Let us consider that scenario and try to write the equation. So, this is where the second reflection occurs and after that the final image is formed, let us consider. So, in this particular case, let us say as this object, as light from this object strikes device 1, let us say it forms an image and let us consider that the image formed by device 1 is something like this. I am just taking a general case, it might be formed on that side also or it might be inverted also. I am just representing it for the derivation, that is it. So, let us consider that the height of this is some hi, or because this is not the final image, I will call this as hi dash. So, intermediate image, because this intermediate image which is formed will act as the object for device 2. So, once light comes from here, strikes this, reflects and goes on to this. So, it appears to come from this particular image which is formed. So, this is the object for the second device, right. So, let us say the image of this is finally formed in this device. It could be formed in front of the mirror, it could be formed behind the mirror. So, I will just for the sake of representation, I will represent it over here and let me represent it something like this. So, let us say this is the final image which is formed. So, let us call it as hi. So, HO is the height of the object, hi dash is the height of the intermediate image which is formed due to first reflection. This acts as the object for the second device and the image formed by that will be the final image according to the case which we have taken, first reflection here and second reflection here. So, let us first see the expression which we write for magnification due to first device. So, what is the magnification produced by the first device? So, the intermediate image which is formed has a height of hi dash. So, according to the definition we can say hi dash divided by HO will be the magnification produced by the first device. Now, similarly, if I write the magnification produced by the second device, so I can write it as the image produced by the second device is hi. So, hi divided by what is the object for this device 2? Hi dash. This I dash is the object for device 2. So, its height should be considered as the object height as far as device 2 is concerned. So, I can write it as hi dash. Okay. So, I have found out the individual magnifications produced at each of these reflections. Now, what we are concerned here is we have placed an object and we have finally attained the image over here, let us say. So, this is our object and this is our image. So, what happens in between is of no concern for us. So, for us the net magnification is nothing but height of the final image which is formed divided by height of the object which we have used. So, this is what we are looking to calculate. So, what I will do here is I will write this hi by ho as hi by hi dash into hi dash by ho. So, I multiplied and divided by hi dash on both numerator and denominator. So, what is the final expression which I will be getting? So, I will be getting net magnification in such a case as hi by hi dash is nothing but m2, hi dash by ho is nothing but m1. So, the final expression which I will get here is m1 into m2. So, this is a very important result. So, whenever successive reflections are happening, so we can say that the net magnification that is produced in such a scenario will be equal to the product of the individual magnifications. So, we can write that down here also. Net magnification is equal to the product of individual magnifications. Produced by each device. So, that is the idea. So, you just have to find the individual magnifications at each and every device and take the product of each one of those. So, that is the case. So, now let us see an example based on this. So, we will take an example. So, we have already seen how to solve multiple reflections in the earlier class. So, we will take one such scenario. So, let us consider we have a concave mirror and another convex mirror. So, let us say we have taken two mirrors like this. So, one is concave and the other one is convex. Let us consider that the focal length of both is 20 centimeters. So, what I have written there are only the magnitudes. You already know the signs which we have to take. I hope you remember that concave will have negative focal length and convex has positive focal length. Okay, anyways. So, let us consider that the separation between these two is 50 centimeters, right, and there is an object which is placed halfway between the two mirrors. So, let us consider that the object is over here. So, a very small object. So, it is placed over there. You can also consider some height for the object. Let us say the height of the object is some 1 millimeter. So, a small object is placed there. Now, just like the earlier case, let us consider two reflections, and after two reflections the final image which is formed, let us try to find the height of that final image. So, I will be using the same concept. I will find the individual magnifications, take the product of individual magnifications, right. So, let us consider the first reflection occurs at the concave mirror and second reflection occurs at convex mirror. So, I will write it down here. This is where the first reflection occurs and this is where the second reflection occurs. Okay. So, let us now draw the ray diagram, or let us write the expression for finding out the image formed in the first mirror, right. So, we can see here the light rays are travelling in this manner. So, as far as this mirror is concerned, this direction is positive, right. So, when I will write it down. So, for first reflection, if I use 1 by u plus 1 by v is equal to 1 by f, and if I substitute the values, so what should be the value of u? Because it is placed halfway, this length will be 25 centimeters, and you know that this direction is positive for this mirror, but the object is on the other side, so I should be using minus 25. So I will be substituting the values 1 by minus 25 plus 1 by v. What is v here? I mean v is what we will have to calculate. So 1 by v is equal to 1 by f. F should be taken as minus 20 because focus will also lie over here for a concave mirror which is on the other side. This is the positive side. So by minus 20. So just simplify that, send this to the other side, you will be getting 25 into 20 by 5 which is 100, but there would be a negative sign. So solving this will give you the value of V as minus 100 centimeters. Okay. So what that means is this minus sign once again indicates that the image of this object is formed on the negative side for this mirror. So because light rays are incident in this direction is the positive direction and this direction will be the negative direction. So minus 100 basically means that the image is formed on this side, right. So for now I will represent this as a point image, point object, and find the location first, then I will use magnification formula to find its final height. Okay. So I will take one light ray which is incident on this mirror like this. So if there is a light ray which is incident in this manner, so what this means is that this light ray will go and converge, or it will go and meet the principal axis at a distance of 100 centimeters in front of the mirror. So this length is already 50 centimeters. So we can say that if I take another 50 centimeters behind, so which is somewhere over here, so somewhere over here, so that is where this light ray goes and meets, or at least tries to go there if that convex mirror was not there. So this light ray after reflection from the concave mirror, it goes like this and it tries to reach this particular position, right. So along with writing the equations, we will simultaneously draw the ray diagram as well, so it will be very clear for us. So first reflection is over. So the light ray which is coming from the first mirror is striking the second mirror in such a way that it is converging at a point which is 50 centimeters behind the second mirror. So this is the incident ray for the second mirror, right. So now what kind of object, you know that the image which is formed by the first mirror, which is this, let me call it as I dash, that will act as the object for the second mirror. So we have been doing this type of analysis till now, right. So this I dash, the image of first, is the object for second. Now what is the nature of that object? You can easily understand, because the incident rays are not actually meeting there, but they appear to meet at that point. So that will behave like a virtual object for the second mirror, right. Okay. Anyways, now let us write the equation for the second reflection. So convex mirror we have this time, I will write the mirror formula once again, 1 by u plus 1 by v is equal to 1 by f. So substituting the values, what is the u value? Remember once again, for the convex mirror, light rays are incident in this direction. So this direction is positive, and you can see that the object is in this direction itself from the pole. So we should consider the object distance as positive. So I will substitute the values, 1 by u value is 50 plus, that should be equal to 1 by v. What is the value of 1 by f? What is the value of f for a convex mirror? That is also given as 20, and you know that focus will be on this side itself, so on the positive side itself. So 1 by 20. Now simplifying that, 1 by 20 minus 1 by 50 will give you v is equal to 50 into 20 by 30. So I will get v is equal to 50 into 20 by 30, so which is 100 by 3. Now you got a positive value there, 100 by 3 centimeters, say positive value. So positive value basically means the image is once again formed on that side, so which means a virtual image once again. So that is what happens here. So 100 by 3 is roughly 33.33 centimeters. So it means that this light ray after striking the convex mirror will get reflected in this manner in such a way that it appears to come from a point somewhere over here, which is at 33.3 centimeters. I hope this is clear. So first light ray has struck the concave mirror. After reflection, it is trying to form an image at this position, but a convex mirror is obstructing it. So this image will act as an object for the convex mirror. It is 50 centimeters behind. So plus 50 is what we have taken as the object distance for convex mirror. So for this object, this convex mirror is forming an image at 100 by 3 centimeters. So which means this light ray after reflection will go away in this direction such that it appears to come from a point which is at 100 by 3 centimeters. So that is the basic idea. So the ray diagram looks like this. Okay. Now we are concerned about finding out the magnification. So let us do that. So let me find the magnification of the first reflection, then second reflection, and then I will take the product of those two magnifications. So first magnification here. We know that minus V by U is the magnification, or you can use F by F minus U also, whichever is convenient. Because we have anyways calculated V, I will use minus V by U. If you just have to find the magnification, you do not need to find V in this case. You can directly use F by F minus U. Anyways, so I will use V minus V by U for magnification. So minus of, now let me substitute the values. Please observe carefully. For the first reflection, what is the object distance? How much is the object distance? This much. It is 25. Should I substitute it as 25 or minus 25? It should be minus 25, because we have seen already this is the positive direction, this is the negative direction, so minus 25. Now what about the image? We already know that the image is formed at minus 100. So from here 100 on that side, so minus 100. So solving this will give me minus minus gets cancelled, 4 minus 4. So yes, I found M1. Now let us find M2. So if I write M2, M2 is equal to, once again the same expression, minus of V by U. So minus of V by U. Now tell me what is the U value for the convex mirror. So for the convex mirror, this is the object, and object is at a distance of 50, right. So 50 plus 50 will be the object distance for the convex mirror. So observe carefully, do not make mistakes with the signs. So just a small mistake here will make the whole question wrong. So you should be very, very careful while substituting the signs of each and every parameter. So plus 50 is the object distance for the convex mirror, and you can tell me what is the image distance also. Image distance is also on that side, which means positive side, and the value which we got is plus 100 by 3. So plus 100 by 3. So yeah, just divide those two terms. What do you get? 2 by 3 with a negative sign. So which means minus 2 by 3. So that is it. We have found the magnifications, individual magnifications. So I can directly write the net magnification now, which is minus 4 into minus 2 by 3. What is that? Plus 8 by 3. So that would be the final answer. So I have given you that the object height is 1 millimeter. So if I have to find the final image height, I can equate this with height of image by height of object, and solving this will give me the height of image as 8 by 3 millimeters. So that should be the answer for this question. So observe carefully what are all the things which we have covered in this particular example. So we have seen how to understand multiple reflections. We have seen how to find the net magnification in successive reflections, right. So students, I have taken the same case which we have discussed earlier, the same scenario. So I have drawn it once again. So concave mirror 20 centimeters, convex mirror, this time the convex mirror's focal length is not known. So, we have to find the value of f such that the image is formed on the object itself. So, we have discussed this concept earlier in the earlier class. So, I want you to once again think about this and you can easily complete this now. So, remember whenever we need to find the location or the condition for image and object coinciding, I told you what should happen somewhere in between. Normal incidence should happen, retraceability should occur, right. So, for retraceability to happen, the light ray should strike the mirror normally. So, because we have just derived the case for the earlier one, I am just using that so that we can easily complete this. So, here this length is once again 25 centimeters, and we have seen in the earlier case that if I find the object location, if I know the object distance as 25, the image which is formed by the concave mirror will be 100 centimeters in front of it. We have just derived that, right. So, I will draw the ray diagram. So, the ray diagram would be like this light ray, if it is incident like this, it goes and strikes this mirror in such a way that it appears to converge at a point which is behind the mirror at 50 centimeters. So, this part we already know, we have just done that. Now, the question is the object has to the image has to be formed on the object itself. So, for that to happen, you know that this incident ray which is striking this mirror should strike normally, and when will a light ray strike a mirror normally? Only when that light ray is the radial line. So, if this light ray is the radial line, which means in other words this light ray should pass through center of curvature. So, that is the condition required for normal incidence, 90 degrees here or 0 angle of incidence. So, if such a scenario is satisfied, I can say that this light ray will once again get reflected back, go to this particular position, once again get reflected back and reach the position of the object once again. So, that is the idea. So, the condition which I have to write now is that this image which is formed by the concave mirror should be formed at the center of curvature of the convex mirror. So, that is the case. So, which means this 50 centimeters should be equal to radius of convex mirror. So, which means 50 centimeters is equal to 2 times focal length of convex mirror. So, radius is nothing but twice the focal length. So, from that I can write the focal length of convex mirror is equal to 25 centimeters, right. So, instead of taking this focal length as 20, if I replace that with a mirror of 25 centimeters, then retraceability happens and the image is formed once again at the location of the object. Now, we will discuss about the velocity of image. So, if there is a spherical mirror and if the object is moving in front of that mirror, you know that the image will also move, whether it is formed in front of the mirror or behind the mirror, the image will also have some velocity. So, we will now find the velocity of that image. So, we already have discussed a similar scenario in the case of plane mirrors. So, I want you to remember that once. So, there what we have done was we have analyzed the perpendicular direction to the mirror separately and the plane of the mirror separately. I hope you remember the results which we have derived. In the perpendicular direction to the mirror, we got the result velocity of image is equal to 2 times velocity of mirror minus velocity of object, and in the parallel direction to the mirror, what did we get? Velocity of image is equal to velocity of object, right. So, we will be doing a similar such derivations now separately for along the principal axis and perpendicular to principal axis. So, let us see that. So, first let us do the derivation for perpendicular to the principal axis and then we will move on to parallel to the principal axis. Along perpendicular to principal axis. Okay. So, I will consider a mirror having some focal length f It need not be a concave mirror, just for representation I am using that. So, let us consider that there is an object somewhere over here at a distance of u, and the image of that will be formed somewhere else. Let us say this is where the image is formed. Okay. Now, if this object has a velocity, so let us say this is the object. If this object has a velocity in this direction, we can say that image will also have some velocity in the perpendicular direction, either upwards or downwards, depending on, we will see what are the factors that determine that. So, for representation I will just write it like this for now. I am not sure whether it goes down or not, just for representation I am using that, right. Now, what I am doing now, please observe carefully. If I assume that this object travels in the vertical direction by a small distance of dy, right. If it travels by a small distance of dy in the vertical direction, or let us call it as dyo, dy of object. Now, if this moves perpendicular to principal axis by a small distance, we can expect that the image also moves perpendicular to the principal axis by some distance, and I will represent that distance as dyi, right. So, that is what I have done. So, I am assuming the object moves by a small distance, image moves by a small distance. Now, you all know that this small distance, instead of considering it as the distance moved by the object, I can also consider that as the height of a different object. If dyo is a height of a particular object, then dyi will be the image height of that object. See, I will repeat once again. If this point object goes from here to this position, let us call O dash, image will move from this position to this position, let us say I dash. Now, instead of taking them as two different positions of object and image, we have done this analysis earlier also. We can consider this whole distance as one object. In that case, this whole distance will be the image height, right. So, that is the concept which I am going to use here, and in such a scenario, if this dyo is the object height and if this dyi is the image height, you all know that I can write dyi by dyo, which is nothing but image height by object height, which is the magnification. This is nothing but m, and you all know how to find the value of m. It can be written as minus of v by u, or it can be written as f by f minus u. So, that is the expression. So, now I will just use this term here, I will rearrange the terms, I will get dyi is equal to m times dyo. Clear? Now, I will divide this with dt on both sides, considering that this object O has travelled by a distance of dyo in dt time. So, in a small dt time, this object has travelled a distance of dyo. So, which means the image has travelled a distance of dyi in the same dt time. So, considering that case, can I say that this dyi by dt is nothing but distance travelled by the image in dt time? I am taking the ratio. So, it will automatically become the velocity of image should be equal to m times, this term will automatically become velocity of object. So, this result which we have derived is only applicable for velocities perpendicular to principal axis. And remember, all these derivations which we are going to do, even this case and the next case, I am doing this by considering that the mirror is at rest, right. So, we will also we can also derive the expressions for when the mirror is moving, right. We are not going to discuss that for now, we can do that later on during our actual class. We will discuss what happens if the mirror also moves. Okay. So, this is the expression. Now, let us do the derivation for along parallel to the principal axis. Okay. So, now let us see. So, let us say the object is over here and the image formed is over here. Now let us say the object has a velocity along the principal axis, some velocity. So if it is at a distance of u, and let us say it moves by some distance of du, it moves by a small distance of du. So if the image is over here at a distance of v, and if it moves by a small distance of dv. Now we already know how to find the relation between these small distances moved along the principal axis. I hope you remember that we have derived that during the longitudinal magnification. I hope. We already know the method for calculating the relation between du and dv. We have already done that during the longitudinal magnification derivation, or else we can once again do that. It is not that difficult also. I can directly write the mirror formula, 1 by u plus 1 by v is equal to 1 by f, and I will just differentiate this expression. When I differentiate this, I will do this time with respect to time, clear. So when I differentiate u with respect to time, I will get minus 1 by u square into du by dt, right. And similarly, when I differentiate 1 by v, I will get minus 1 by v square into dv by dt is equal to, you know that focal length of a mirror will anyways be constant, it does not change with the motion of object and image. So this is 0. Now if you observe here, this is rate of change of u, the rate at which this length is changing represents the speed with which the object is moving, clear. And similarly, this dv by dt represents the rate at which this v is either increasing or decreasing, and that represents the speed with which the image is moving. So this is nothing but velocity of object, and this term here is nothing but velocity of image. Whatever I am doing is along the principal axis, right. So just rearrange the terms. You will be getting vi is equal to minus v square by u square into v naught, right. So this is the expression finally, and I can write this term which you see here, vi is equal to this term v by u whole square. I can write it as minus of m square into v naught. So this is the final relation between velocity of object and velocity of image along the principal axis, and this is the relation between them when the velocities are perpendicular to principal axis. So if there is an object which is moving at some random angle, let us say at some angle like this, it has both the components. It has a perpendicular component as well as a parallel component. So for finding the perpendicular component of velocity of the image, you have to use this formula, and for finding the parallel component of velocity of the image, you have to use that formula. So that is the basic idea. So please remember them. So here you have m into v naught, and there you have minus m square into v naught. Now once again, I have reminded you this earlier also during longitudinal magnification. This term is always positive, sorry, this term, whole term is always negative. M square is positive into minus, this whole term is always negative, which means that you can understand that VO and VI are always opposite to each other. So if the object in this case moves in this direction, then the image should move in the opposite direction, and vice versa. So the directions should always be opposite to each other. So this is very, very important result. Maybe I will write it down as well. Object and image will move in opposite directions along principal axis, right. Now we will see some examples based on this idea. So students, let us see this question based on the concepts which we discussed now. So they have given a concave mirror having a radius of 60 centimeters. There is a point object placed at a distance of 40 centimeters, and they have given that this object at this moment has this much velocity. So, I cap minus j cap plus 2k cap, and they are asking us to find out what is the velocity of image, and for the reference they have given the directions of x, y, z axis. So, this is x axis, y axis and z axis. So, remember that a mirror is basically a 3-dimensional structure. Although we are representing it in 2 dimensions, keep in mind that it is a 3-dimensional structure. So, I have told you about the aperture earlier. So, it has a circular aperture like this. So, it looks like a bowl, right. So, it looks like this in the form of a bowl. So, this is the principal axis, and in this particular case we can say that both y direction and z direction are perpendicular to principal axis, correct. X direction is along the principal axis, whereas y and z both are perpendicular to principal axis. So, we can say both y and z are perpendicular to principal axis, and for finding velocity we know that we have different methods for different directions. Along principal axis we use minus m square, right, and for perpendicular to principal axis we use m. Okay. So, let us try to find out the m value first, the lateral magnification. We already directly have a formula for lateral magnification, which is m is equal to f by f minus u. So, let us substitute the value directly in that. So, what is the focal length of this mirror? 30, but because it is a concave mirror, focus is on this side, which means we should take negative. In this case, this direction is positive. Okay. So, f I will substitute it as minus 30 divided by f, once again minus 30 minus u. We know that u object is on this side, whereas this is the positive direction. So, minus 40. So, solving this will give us minus 30 by plus 10, right, which is minus 3. So, that is the magnification. So, now using this I will find the velocity of the image perpendicular to principal axis. So, we know that velocity of image is equal to m times velocity of object. This is perpendicular to PA, correct. So, let me substitute the values. So, I can write m, we got the value of m as minus 3 into what is the velocity of object perpendicular to principal axis. So, I have told you that this is the component along the principal axis and this is the component perpendicular to principal axis, correct. So, I will substitute the value of object's velocity perpendicular, which is minus j cap plus 2k cap. Solving this will give me 3 j cap minus 6k cap. So, that would be the velocity perpendicular to principal axis for the image. Now, similarly we know the formula for along principal axis, right. So, we know that velocity of image can be written as minus m square times velocity of object, and this is the expression we use for parallel to principal axis, clear. So, now substituting the values once again, I will be getting this as minus of m square is minus 3 square, which is 9 into velocity of object. What is the velocity of object along principal axis? It is just I cap. So, I cap. So, this will give me minus 9 I cap. So, that is it. We got both the components of the image velocity. So, I can finally write velocity of image is equal to minus 9 I cap plus 3 j cap minus 6k cap. So, this will be the final answer. So, in this particular case, if you observe, we have calculated the velocity of image considering that the object is on principal axis. So, whatever derivations we have done is only applicable if the object is on the principal axis. If it is somewhere else, if the object is somewhere over here and moving in some other direction, so in such a case we can't use this formula, clear. So, this is only when the object is on the principal axis, keep that in mind. So, we will discuss all these also later on during our usual class. If the object is not on the principal axis, somewhere over here moving in some direction, and if the mirror is also moving, so in such a case how to find velocity of image. So, that will be a discussion for later. Students, now we will discuss about this concept of the effect of removing a part of the mirror and what kind of effect does it produce in the image which is created, which is formed. So, we have discussed a similar scenario in the case of a plane mirror. I hope you remember that if I have a plane mirror and there is an object, the image will be formed behind at the same distance. Even if I cut and remove one part of the mirror, the location of the image will not change. The only thing that changes would be the intensity of it, the brightness of it, and the field of view from which the image can be observed, right. So, in the same manner, let us see what kind of effect is formed in this case. So, object is over here and image is over here, let us say. I hope you remember when such a scenario occurs. Do you remember that? When will a concave mirror form an object image situation like this? Do you remember? So, this case forms when object is between center and infinity and image will be formed between center and focus. So, please be aware of all these. So, the initial ray diagrams which we have drawn are very important. Understanding the nature of images is also very important. So, you should be very clear about that. Okay, let us come back to this. So, in this case, if you look at the ray diagrams, it would be something like this. So, this incident ray will get reflected and reach the image. Another incident ray here will get reflected and reach the image. So, similarly, you can take one more incident ray like this, it gets reflected and it will reach the image, right. You can take some light rays below the principal axis as well, similar to that, right. So, one more light ray here, it gets reflected from here and converge at the image. So, this is what happens. So, that is how the image formation generally occurs. Now, think of a scenario like where I have removed the lower half of the mirror. Let me write it down. If the lower half of the mirror is removed. So, now can you guess what will happen in this scenario? Will the location of the image change? Will the location of the image change? No, because you can still see what is happening with the remaining part of the mirror. The remaining part of the mirror, the reflections will occur in the exact same manner as they were happening earlier. So, even if I remove this part of the mirror, so this will still be happening in the same way, which means the location of the image will not change. But what will change? The brightness of the image, because earlier you can see that there are rays coming from each part of the mirror converging over here. So, large number of rays will converge here to form the image, but if the lower half is removed, only rays from the upper half will converge to form the image. So, what happens in that case, in this particular case, is that the image, the location of the image, the location of image does not change, but what changes? Its brightness changes. Clear? So, that is the idea. This is not just with the lower half, you can understand it in, you can remove any part of the mirror. So, you can, let us say I have cut this mirror, let us say, if I cut this into different parts. So, this is one mirror, this is one mirror, this is one mirror. So, I have made that mirror into 4 parts now. I hope you can see the gaps over here. So, I have cut that mirror into 4 parts, let us say. So, what we can say is, if I cut it into 4 parts and if I do not change its positions, as long as the mirror is in the same orientation where it is earlier, if I just cut it and place it at the same position where it was, we can say that each of these 4 parts of the mirror will form the image at this position itself, because none of the reflections happening at those mirrors are changing, right. So, just by cutting some part, if you are not separating them, nothing will happen to the image, but if you separate them, then the image location might change. So, let us see what happens when I separate them. Clear? So, let us consider a scenario where I am separating it, right. So, in this case what happened was, so the mirror was initially like this. I have cut the mirror into 2 parts. So, now this is only the upper half of the mirror. So, I am not showing you the lower half of the mirror, that is the upper half. Now, think of a case, the object is over here. So, this is the principal axis, correct? The object is over here. Now, what will happen if I shift the mirror? Now, think of it. If I shift the mirror from this position parallel, or perpendicular to the principal axis, if I move it vertically upwards. So, to represent that, I will use a different color here. So, I will represent the new position of the mirror with blue. So, let us say this is the new position of the mirror. So, the mirror is finally like this. So, let us just consider a scenario like that. So, which means I have just shifted the mirror vertically upwards, or let me draw this principal axis also in black. So, this was the initial position of the mirror, right. Now, what I have done was I have just shifted the mirror upwards. I am not changing the location of the object. Now, what will happen in this case? Will the image of this object change? It will definitely change, and the reason for that is, this is one very important concept which you will have to keep in mind. As the mirror is shifted in this manner, it takes its principal axis also along with it. The principal axis will also shift along with the mirror. So, as a result of that, the new principal axis will now be over here. So, this is how the new principal axis will be. So, please observe the colors here. So, the black represents the initial position of the mirror and the blue represents the final position of the mirror. So, what you will have to observe here is that the principal axis also has shifted along with the mirror, right. So, that is the basic idea. So, now if you have to find out where the final image is formed, you will have to consider this object, because this object is not on the principal axis, and you know how to deal with cases where the object is not on the principal axis. You will consider it as an extended object and then find the final location of image. So, you will have to consider it as an extended object, find the image distance, find the magnification and find the final location of the image. So, that is the method which we will have to use whenever the mirror is shifted, clear. So, I will write it down here. If the mirror is shifted perpendicular to the principal axis, then the principal axis will also move to a new position. Clear? And to find the image, you should be considering this object as an extended object and use the magnification method to find the final image. So, that is the basic idea, right. So, when you just cut the mirror into different parts without changing the positions of the mirror, so each part will still form the image over here. But the moment you cut the mirror or you just shift the mirror perpendicular to the principal axis will also shift. So, when the principal axis also shifts, the object is no more on the principal axis. So, it should be considered as an extended object and you can use magnification method, right. So, students, let us see an example based on the earlier concept. So, here it is given that there is a mirror, concave mirror of radius of curvature 30 centimeters. So, it was cut at the center along the principal axis. It was made into two halves and the two halves were separated away perpendicular to the principal axis by 1 millimeter each. So, if these are the two mirrors, so they have cut it at the center and this was moved by 1 millimeter and this was moved by 1 millimeter, and you know that each half will have a new principal axis. Now, it takes its own principal axis along with it, right. You can understand it that way. So, now the object will remain at the same original position of the old principal axis. So, this is where the object is. So, as a result of the mirrors being moved apart, what happens is that the image of this in this mirror and the image of this in this mirror will be formed at different positions, right. So, they are formed at different positions. So, we need to find out where those two final images are formed and what is the separation between the two final images. So, let us try to understand this. So, I have told you just earlier, because this object is now not on the principal axis is shifted, we need to consider it as an extended object for both cases. So, first let me do for one, the same thing repeats for the other because it is a symmetrical scenario. So, the object is at a distance of 20 centimeters and we have the radius of curvature as 30. So, which means focal length is 15 centimeters. Now, let us find the magnification. So, how do we write the expression for magnification? M is equal to F by F minus U. So, what I get here is F should be taken as minus 15 because it is a concave mirror. Once again minus 15 minus U, U is minus 20. So, it is on this side. This direction is positive. Light goes in this direction. So, this becomes plus 20 and the final value which I get is minus 3. So, the magnification is minus 3. So, it will automatically mean that you can also equate this with minus V by U and find the value of V also. So, you get the value of V is equal to minus and minus will get cancelled. So, 3 times U. So, which means V is equal to 3 times minus 20, which is minus 60 centimeters, correct. You can also use the mirror formula to calculate V because anyways I have found the magnification, I continued with that. Okay. So, because this is 20, we can say that image will be formed for this object at 60 centimeters. So, let us say it is somewhere over here. So, the image of this will be formed at 60 centimeters. Now, look at how it is formed. The magnification is minus 3. So, 3 means the size will become 3 times and minus means that it is inverted. Now, if you see, I am doing with the upper half of the mirror. So, for this upper half of the mirror, the object is downwards, the object is below the principal axis, which means magnification of minus 3 will mean that this image is becoming 3 times bigger and also changing its sense, changing its position from below the principal axis to above the principal axis, which means that the image of this will be finally formed over here above the principal axis in this manner, and because this is 1 millimeter in length, this will be 3 millimeters in length. This will be at a distance of 60 centimeters. So, if this is O, we can say that this is the point where O dash will be formed in the first mirror. I hope this is clear. So, it is formed at a distance of 60 centimeters in front of the mirror. Now, this is the principal axis, the black line which you see here. So, this will be the principal axis. So, the object is 1 millimeter below the principal axis. So, here it should be 3 millimeters above the principal axis because of the negative sign. So, this is where the final image is formed, right. Now, by using the same logic, we can say that the mirror which is at the bottom will form the image once again at the same distance by the same length, and for this the object is above the principal axis. So, it will form its image below the principal axis. Once again it will be 3 millimeters. So, let us call it as O double dash. So, that is what will happen. So, the image of this object will be formed by this mirror over here, will be formed by this mirror over here. Now, the question asks what is the separation between the two images. So, we can directly write the separation is equal to, you can see that clearly in the diagram itself, 3 millimeters, 1 millimeter, 1 millimeter, 3 millimeters. So, totally it is equal to 8 millimeters. So, that should be the answer, right. So, students, we have covered almost all the concepts related to spherical mirrors. So, there is one particular area where I want you to focus more, especially understanding the nature of images formed. So, we have understood that by using ray diagrams. There is also another method for understanding that by using the graph between U versus V. I have not taught that to you now, So, whenever you come across that u versus v graph, you can skip that for now. We will anyways discuss that in the coming classes also. So, do not worry about that. So, what I am going to tell you now is basically a way of understanding how a virtual real image is formed, what is the basic idea behind it. So, I want you to listen to this carefully. So, this will help you in understanding the nature of images every time. So, please focus. So, let us consider a concave mirror. So, let us say that there is a concave mirror and there is an object somewhere over here, right. So, I will give you few cases here. First case is real object, real image. Second case is real object, virtual image. Third case is virtual object, real image. Fourth case is virtual object, virtual image. Now, one important thing you will have to know about a concave mirror is that concave mirror can undergo out of these 4 cases 3, but it cannot form the 4th case. One of these 4th cases is not possible in the case of a concave mirror, right. I will tell you which one that is. I also want you to pause here and think about which of those 4 cases is not going to happen in the case of a concave mirror, right. So, that case which is not formed will be this one. A concave mirror cannot form a virtual image for a virtual object, right. Now, understanding this is very, very important. So, please observe carefully. Let us first understand what a virtual object means. By now, you have a basic idea that we use the term virtual object when the light rays are not actually coming from an object, starting from an object and coming in a diverging manner, but actually striking the mirror in a converging manner. So, whenever light rays are converging rays, when the incident rays are converging, they appear to meet behind the mirror, and that position is what we call as the virtual object, right. So, this idea we have, virtual object means converging incident rays, right. Now, what do we mean by a virtual image? When is a virtual image formed? Let us try to understand. See, if I consider a light ray which is incident like this, it might get reflected like this and meet here. So, let us draw one more ray. Now, what type of image is being formed here? Is it virtual image or a real image? It is a real image, and the reason why it is a real image is because it is actually formed by intersection of 2 rays, 2 actual rays. So, which means if the reflected beam is a converging beam, then the image formed is a real image. Otherwise, if I consider a scenario like this, where after reflection from the mirror, if the light rays are travelling in this manner, so if these are the reflected rays. So, now if you see these 2 reflected rays, they are not going to actually intersect to form an image, but when I extend them backwards, they appear to intersect over here, and that is what we call as a virtual image, right. So, when is a virtual image formed? When the light rays are diverging. So, this means diverging reflected rays, that is it. Now, you will get the idea. Why can't a concave mirror make this happen? What I will tell you what this means. What it means is that a concave mirror cannot make a converging incident beam into a diverging reflected beam. So, what that means is, if the light beam which is incident on a concave mirror is a converging beam. So, let us say if this is the concave mirror, and if the beam of light which is incident on it is a converging beam, it can never make a converging beam into a diverging beam. You know the reason? Because concave mirror is a converging mirror. So, already the light rays are converging, mirror will further try to converge. So, the light rays which are reflected will be even more converged, they can never become a diverging beam, and that is the reason why this case is not possible. All the other cases are possible. So, what does real object mean? Real object mean diverging incident rays. What does real image mean? Virtual image means diverging reflected rays, real image means converging reflected rays. Now think, can a concave mirror make diverging incident beam into a converging reflected beam? Yes, that is what is the diagram which I have drawn here. Correct? So, that is the basic idea. That is how you should understand the nature of a particular mirror. So, concave mirror is a converging mirror. So, when something is already converging, it will further converge. So, it cannot diverge. So, that is the reason a concave mirror cannot form this particular scenario. So, I'll write it down over here. A concave mirror cannot form a virtual image for a virtual object. Clear? And I hope you understood the reason why. Clear? Because a concave mirror is basically a converging mirror. So, what we can say is the reason for this can be written like this: a converging beam cannot be diverging, cannot be diverged after reflection from a concave mirror. Clear? So, concave mirror has it doesn't have that ability. So, because it is a converging mirror, it tries to converge all the time. So, when something which is converging will be further converged. So, that is the basic idea. In the same manner, you can also think for a convex mirror. I want you to write down a scenario like this, right, and try to think about which of these 4 cases is not possible for a convex mirror. Even a convex mirror can do 3 of these 4 and it cannot do one of those 4. I will give you the answer for that. I want you to make a similar kind of analysis and write down a similar kind of reason in your notes. Clear? And the case which convex mirror cannot perform is this. Clear? So, please analyze that just like we have analyzed here for a concave mirror. So, just like we have written some points for the concave mirror, write down similar points for convex mirror. So, I hope to see that in your notes.